Dane began surveying in 2005, and the ability to be outside, perform historical research, and etc. drove him to the land survey profession. He received his surveying training in 2007, subsequently became a professional land surveyor in the state of Maine in 2009. And Dane is not only licensed in Maine, but Vermont, Texas, Colorado, and Oregon. If you can't tell, Dane has a passion for teaching. It was through teaching classes for up-and-coming surveyors that he discovered the gap in available education materials. Over the next few months, Dane took pages and pages of teaching notes and incorporated them into a manual to assist further surveyors gaining the knowledge necessary to pass the NCES Fundamentals of Surveying Exam, or the FS. And a culmination of his work called Fundamentals of Surveying Exam Study Manual is available for purchase, and I'll throw that link in there as well. And we talk about it every time Dane is on here. He's got video instructions as well that goes with the videos that we did for WestFed. So our Western 13 states, we have a WestFed organization, and Dane has a whole video series that goes with his book as well. So if you're looking for video over self-study, you can certainly purchase that. I think it's $199 if you're a WestFed state. So anybody in the West, and I think it's $299 if you're outside of the West Coast. So we should be good. Let me let one more in, and then so Dane's doing intersecting lines tonight, and then he'll be back again next month, again for some other FS type stuff. And as he said, he's been developing more and more all the time. So as always, Dane, I appreciate your time and support and your love for doing this. That's awesome.
Yeah, thank you very much.
Of course.
Yeah, I saw Michael had my book, so I appreciate the support.
Yeah.
Yeah, everybody, thanks for having me. So we're going to get into intersecting lines today. And the purpose of this is you're going to utilize this whenever you're figuring out the center of a section or the center of quarter sections in the PLSS system. So when you're finding the centers of a section or the center of a quarter section or a quarter or a quarter section, you're going to be intersecting lines. It's not, you will not be using double single proportioning. Okay. Like I always say with double single proportioning, this method should not be used to calculate a corner if that corner is already existing. Okay. So just like with single double proportioning, you should not be using math at all unless it's your last case resort and you have no center monument, you have no evidence of that monument, the monument is completely lost. All right. At that point, that's when you would start resorting to math. When you do use math for section corners, center corner, whatever it is, it's almost guaranteed that your mathematical calculation will not be the corner that was originally intended to be, that was originally set by that original survey. The reason you're doing the math is because it's your best guess at the situation. So, just let it be known that when you're using math in survey, something's drastically wrong. All right. You're not finding what you need to find, and you're having to resort to mathematics to give you that answer. And that is not going to be the answer of that original corner, but it's going to be the best you have. There's all kinds of evidence that you can use to get a corner back in. You can use reference ties, a disturbed monuments location, bearing trees. I mean, it goes on and on and on. All the evidence should all be exhausted before you do any of this math. So I just want to make sure everyone understands that it shouldn't be the first thing you jump to. It should be the last. Okay. Like Trent said, I do love teaching. I was actually I am a licensed Montessori teacher. I did it, got my license, did it for a year, and then immediately quit because I couldn't handle the parents. But the kids were awesome. I was just a young guy. I was like 25, 24 years old. I was living in Houston, and I got my license, and I just figured it wasn't for me. But that love for teaching has never really gone away. And when I see the word intersecting lines, the words intersecting lines, I always think I had a student. He was just like probably 6 or 7 year old, and his name was Azar. And this little kid was so highly intelligent that it was almost to his disadvantage. He was always bored in class and stuff. You know, I was always trying to give him stuff on the side. Um, well, one day I was teaching him geometry about intersecting lines, and he wouldn't stop talking and disrupting. So I asked him to go sit somewhere else, and I would come talk to him in a minute. Well, when I went and talked with him, he had these two lines drawn on his paper, and they were intersecting at one point. And he said, Mr. Dane, you and I are like intersecting lines. We're always going in two different directions, but we always meet at one point. And so on top of being a mathematician at the age of 7, he was a little poet too. But he has it exactly right. Two lines going in two different directions. If you have that situation, you will have a point where those two lines intersect, and it's only going to happen at one single point. Okay, and our problem tonight is going to show how to figure out what that point is. If you're giving a bearing, if you're given a bearing and a bearing, then we can figure out that intersecting point. Sometimes they don't give you a bearing. Sometimes they'll give you 2 points over here, 2 points over here. And from those coordinates, we're going to have to generate a bearing. And then from those coordinates, we'll have 2 bearings, and then we can get the point. So let's get into it.
Dane, before you
yeah.
do that, so those with all the view, like the gallery and the view. So Dane has two things. One, he shares the PowerPoint, and so that's like the main screen. But then if you right click on the one that he has just his little piece of paper there and the pencil, and if you right up on that little 3 dots up on the top, you can say pin view. That way those two are just a side-by-side view. You can make your screen bigger or larger so that you can kind of flip back and forth between the two of them there. But if you want to pin his one with the word piece of paper on there, that'd be good for you guys to be able to watch and follow along on both pages there.
All right. So everyone should see a yellow screen with intersecting lines, and then my hands with a cross. Okay. All right. So first off, like I said before, you use this process to solve for the center of a section or the center of a quarter section. I think I've done single double proportioning here, but that's single double proportioning would be finding the section corners and the quarter section corners of a section. Now, I don't want to get too far into that, but you would not use double proportioning on section corners that are on a township corner. Those would be simple single proportionings. Okay. So you use double proportioning when you're finding section corners, and those section corners are not on township corners, or I'm sorry, not on township lines. You would use single proportioning for everything else except for the centers, which is what we're doing now. So to find the center, you would have to do your single double proportioning methods to identify the 4 quarter corners of a section. Okay. Now, how you go about doing that can vary greatly. You might go out there and get lucky, and you might find all 4 of these. Okay. Odds are you won't. If you don't, let's say you don't find this east quarter. Okay. Let's say that one's missing. Well, in order to find that, you're going to have to resolve the northeast corner of the section and the southeast corner of the section. And once you have those two located, then you can single proportion between them to back this quarter corner back in. And this problem can keep extending further and further out. What if you don't have the information for this quarter, for this section corner? What if you don't have this quarter and this quarter? Well, you might have to go to this section corner down here and this section corner over here in order to get it in, okay? So you got to utilize what's nearest to you and back it in until you get to the point where you have finally your 4 quarter corners. Your north, your south, your east, and your west quarter corners, okay? Once you have those 4 in, again, the journey to get to that point could be very simple or it could be pretty elaborate. But once you have these 4 in, you're simply just going to draw your line between the north and the south, your line between your east and your west. And it's very simple. Where they cross is going to be your center. Okay. And that's what we're going to be doing tonight. Does anyone have any questions about this before we move on? All right. In sectionalized lands, typically, though exceptions do exist, the center of a section or the center of a quarter section are established by the intersection of lines. The intersection of lines produces a point of intersection. The methods in this session will outline the process of identifying the coordinates of the intersection point for the 2 intersecting lines. Now, the only way lines will not intersect is if they're perfectly parallel, okay? If you have 2 lines and their bearings or their azimuths are ever so slightly different, they will intersect at some point in time or at some point, you know. The closer they are in their bearing or their direction, the longer the lines will have to be for them to intersect. Now, in this situation, they almost are at 90 degrees. So it's pretty, their intersection is going to be pretty prevalent, okay? The process on how you find out what the intersection is, it's a 3-part process, actually 4. But first, we got to figure out what slope is of each line. I'll go through that. Then we're going to figure out the y-intercept of each line. That's going to be where do these lines cross the y-axis. Then we're going to have to stay organized with our process here. This is pretty simple math. The hardest part is staying organized, okay? And that's the case with a lot of the math that we do. It's pretty simple math: addition, subtraction, multiplication, and division. But the order and how you stay organized really sets the stage, okay? So process 3 is going to be doing 2 sets of equations. And I'm going to show you how to go about doing that and staying organized, okay? Equations times 2. All right, slope first. So first off, what is slope, okay? I like to think of it like stairs. So you have a staircase, and when you're building stairs, there's a thing called rise and there's a thing called run, okay? Rise is how far up does the step go, and the run is how far in does the step intrude, like where you put your foot, okay? When you're building a house, whatever, there's going to be regulations in your county that tells you a step cannot have a run of it cannot have a rise greater than X if the run is less than Y or something like that, okay? But all they're trying to say is they're trying to set up this ratio of how high a step is compared to how long a step is, okay? So in this situation, let's say these steps go up 2 feet and the run is 1 foot, okay? So I'm gonna go up 2 foot, 1 foot in, up 2 foot, 1 foot in, up 2 foot, 1 foot in. So slope is considered to be the change in y divided by the change in x. What does that mean? Well, y, if you think about it on the Cartesian graph, you have a y-axis and your x-axis. Y is how much is it going to change going in a northerly direction or along the y-axis. And x is going to be how much is it changing in a easterly direction and along the x-axis. Okay. Well, in this situation, from this point here to this point here, I changed in a northerly direction along my y-axis. I changed 1, 2, 3 rises. Each rise is 2 feet. So I changed 6, 2, 4, 6. I went up 2, up 2, up 2, 6. Then how much did I change in an easterly direction or along my x-axis? I went in 1, in 1, in 1. So that's 1, 2, 3. So my rise over run is 6 over 3, which would be equal to 2. Okay. So this situation, I would have a slope of 2. Does everyone understand that? Now, it's pretty easy to understand with the steps, but let's say we were given coordinates for this point here and this point here. Well, it's going to be just as easy. Let's say this point had a coordinate of 0, 0. And this point up here would have a coordinate of 3, 6. Okay. So now I have 2 points, 0, 0, and 3, 6. These are x and y, x and y. So now my change in x really does make sense, because how much do I change in just y? It'll be 6 minus 0 equals 6. And my change in x would be 3 minus 0 equals 3. Okay, so it's the same number. So I just wanted to show it to you in coordinate form, essentially. Before I go any further too, I want to make sure that you guys do not confuse x and y with northing and easting. So x and y coordinates are really written in easting northing format, right? Northing is equivalent to your y-axis, how far up and down you go north and south, and easting is how you go east and west along your x-axis. So if they provide you a coordinate and it's northing easting, you have a northing and an easting of 5,201 and an easting of 7,629. Well, essentially, this is north x, y, so it should be written as 7,629,5,201. Okay, so don't get those two confused. You might know how to do all this math that we're about to talk about, and if you flip these, everything's going to be wrong. Okay, so please don't let that be the reason you don't succeed at this. So in order for us to find intersecting lines, there has to be 2 lines. All right. So they're going to give us a coordinate. They're going to give us a coordinate. Then they're going to give us another line with a coordinate and a coordinate. We're going to have to separate and stay organized and designate one of these lines as line 1 and the other one as line 2. And we cannot let the information from one enter where we're trying to figure out the information for the other. Okay. So we're going to have to keep line 1's coordinates separate from line 2's. And we're going to have to do everything twice. We're going to have to figure out 2 slopes. We're going to have to figure out 2 y-intercepts. And then we're going to set all that information equal to each other to reveal the answer. Okay? So in this situation, we did 0, 0, and 3, 6. All right. Now, as you saw me do a little while ago, I subtracted point A from point B to get my slope. Okay. I did 3 minus 0 and 6 minus 0. Okay. That's fine. I could have done 0 minus 3 and 0 minus 6 if I wanted. I would have got -6 and -3. I would have still got a slope of 2. So it doesn't matter which way I do it, but I do have to make sure that my whatever point I designate as to be the first point, I'm going to have to keep it that way. Okay. So again, I could have done 3 minus 0 and 6 minus 0, change in y, change in x. I would get 6, 3 equals 2. This was point, I did point A first and then point B, and I have to do A first here and then point B. But let's say I would flip it. Change in y would be 0 minus 6. Change in x, 0 minus 3. I get -6, -3. I still get 2. But in this case, I did B first and then A, B first and then A. Okay. I can't do 0 minus 6 and then 3 minus 2. I'm sorry, 0 minus 6 and then 3 minus 0, because then I'll get -6 over 3. Now I'll get a slope of -2, which is not correct. So all I'm saying is stay in order. Doesn't matter what you put first. Point A I did first, point A I did first, and then B comes, I flipped it here. But it doesn't matter which way I do it as long as I stay consistent, okay? And I can do it this way on this line, and then I can do it the other way on this line. It doesn't matter, okay? The only thing is that you stay consistent within each slope calculation. So negative slope versus positive slope. Think about how it, think about it like you read, okay? You read from left to right. Well, if the line is going down in a left to right motion, that is going to be negative slope. If the line is going upwards from a left to right motion, that's going to be a positive slope, okay? So when you're doing these calculations, one way to check if you're staying consistent is if I'm figuring out this line right here, which is what I've been doing, moving from left to right, I'm going up. So I know my calculation for my slope of this line, it better be a positive number. And sure enough, it is, okay? So use this notion whenever you're doing these calculations as a good check, all right? You should know what negative slope looks like and what positive slope looks like. I like to think of it like you read. You're reading from left to right. If you're gaining from left to right, it's positive. If you're losing from left to right, it's negative. If you're going down or losing, negative, up or gaining, it's positive. All right? So that's slope. And again, you'll have to do this for each line. I'm going to follow up with this as a example. So we'll use this in real life, okay? The next thing is y-intercept. So this is slope, M. The next thing we said was y-intercept. Y-intercept, simply put, is where does our line, we have two of them, but where does this line cross the y-axis? Okay, let's take that same line with 0, 0, and what was it, 6, 3, 3, 6, sorry, 3, 6, okay? So this one's an easy one to figure out because I have a point. One of my points is on the y-axis. So I know my y-axis intercept, my y-intercept of this line is 0. Where does this line cross the y-axis? That's what I'm asking, okay? Let's do one that's not so relevant. I mean, not so easy, okay? Let's say, well, let's continue this line, all right, on that same path. I know from this point, I'm going to have to go down 2 and over 1 to create my next point, because that's what I've been doing this whole time. Down 2 over 1, down 2 over 1, down 2 over 1. Well, down 2 over 1, that would make this point. Let's say they didn't give us the 0, 0. Let's say they gave us -2 and -1. So it'd be -1, -2. Okay. So if they gave us a line with -1, -2, and 3, 6, we would have to figure out where does that line cross the y-axis. Well, in this situation, it's going to cross it at the 0 mark on the y. Okay. Let's figure out. Remember, the slope of that first line was 2. Let's see if this still is 2. So change in y over change in x. Change in y, 6 minus -2, 6 plus 2, essentially. Staying consistent, 3 minus -1 would be 3 plus 1. Now I have 8 over 4. My slope still is 2, okay? And it will continue to be 2 as long as I keep it staying on that same direction, bearing, azimuth, whatever it may be, okay? All right, so where a line crosses the the y-axis, that's called the y-intercept, and the formula for that is B, which is y-intercept, equals a y value minus mx. All right. So to figure this out, I need to know my slope, and I need to have some x and y values. I can use any point, and I have an infinite amount of points that I can use along this line to plug in right here. And if I give it my slope and I tell it just one point with my x and y value, it's going to generate my y-intercept. Okay, on this line, we know three points. We know 0, 0, we know -1, -2, and we know 3, 6. Let's use 3, 6. So I know my y value is going to be 6. I know my x value is 3. And we already figured out slope from step 1, which is 2. So this would be written as B equals 6 minus 2 times 3. 6 minus 6 equals 0. So B equals 0. So what this is saying is this line crosses the y-axis at value 0, which is true. Okay? And this works with any point I put in there. Let's try it again with point -1, -2. B equals -2 minus my slope times x value of -1. Okay, B equals -2 minus 2, which would be -2 plus 2, b equals 0 again. So it will equal 0 with any point you plug in along this entire line. There's an infinite amount of points, okay? So you have to, in order for that to work, you're going to have to know slope, and that's why it's step 1. After that, plug in any x and y value of any point, and then you'll be able to figure out your y-intercept, okay? Again, this is going to have to happen twice. I have to figure out my slope on each line and my y-intercept on each line. So I'm actually doing 4 things. I'm doing slope 1, slope 2, y-intercept 1, y-intercept 2. All right, so that was step 2. Is everyone following so far? I don't mind if y'all have questions. All right.
Nothing yet. Thomas had a earlier comment about the east-west line being on a curve when you're dealing with obviously center sections and that kind of stuff, but we can revert back to that.
Isn't the east-west line a curve?
Because you're thinking BLM on an arc, right? So that's what Thomas is.
Oh, yeah.
So we can get back to that later, but that was the only thing so far in the chat. So
all right. Okay. Let me see. So first step, slope. Second step, y-intercept. Third step. Okay. Now what we're going to do here. Let me go back up. Hold on. All right. So there's a slope so there's a y-intercept form of a line, which is b equals y minus mx. Okay, that was right there. That's the y-intercept form. We're just going to keep playing with this equation and solving for different items in this equation, and then they change the name. That's all that's occurring, okay? So the next form of the equation is the slope-intercept form. Slope-intercept form. And that one is x or y equals mx plus b, okay? So this is the same equation. I'm just solving for y now as opposed to my y-intercept, which is b, okay? Y equals mx plus b. So if I know my slope and I know my y-intercept, all I'm going to have to plug in is an x value of any point, and it's going to give me the y value of that point. Well, if I were to set line 1's slope-intercept value equal to line 2's slope-intercept value, what I'm saying is when I do this for line 1 equals the slope-intercept of line 2, I'm saying, where do my 2 lines share a y value? Okay? Essentially, I'm making these equations tell me where the lines intersect, and then I'm going to ask it, not only where do they intersect, but what is the y value of where they intersect? Okay? Because I know this line 1, will equal the y value of line 2 only at one point. And that one point is going to be where they intersect, right? So if I set these 2 equations equal to each other, I'm going to be able to figure out, because they are equal, the y of line 1 at the intersection point will equal the y of line 2 at that same intersection point. So they will equal each other at only one place, and that's where they intersect. So if I fill in the information for line 1 here and line 2 here, and I solve this equation solving for x, I'm going to find my x value of where these two lines intersect. So let's do it. Well, no, we're not going to do it yet. I'm going to do it in the example. All right. And then the final thing we do is once we figure out this x value, we're simply just going to plug that value back into one of these forms to solve for the y value. So we're going to solve for the x value first. Now that we know that, now when we use this equation, y equals mx plus b, and now I know this, and I know this, so I can just get my y value. And then I'll have my x and my y. That'll be the intersecting point. So let's go do an example. All right. Let's say we have this situation right here. We have two lines. Okay. Line 1 is going to be this one. I designate that right up front. Okay. I can make it line 2. I can make it line 1. It doesn't matter as long as I stay consistent. Line 2. All right. And I know only 2 points on each of these lines. On line 1, I have a point that is number 1, 5, xy, and 15, 10. Line 2, I only have 2 points, and they are 4, 11, and 10, 5. Okay. So step 1 was to find the slopes of both lines. So let's do that. Line 1, it's going to be change in y over change in x, and I'm going to be staying consistent when I do this. Okay. I'm going to use this point first always. So it's going to be 10 minus 5 over 15 minus 1. That'll be 5 and 14. Making sure I'm doing this right. It'll be equal to 0.357. Let me make sure that's right. Because I did it backwards in the example. 10 minus 5 equals that, divided by 15 minus 1. Something's wrong. Let me make sure. 10 minus 5, 15 minus 1. 5 divided by 14. Yeah, that's right. Okay, so I chose point A, let's say, and point B. So A's are always going to go first, and B's are going to go second. 10 minus 5, 15 minus 1. So this is my slope for line 1. Line 2, all right, change in y over change in x. I'm going to make this point A, make this point B. So it'll be 11 minus 5 and 4 minus 10. This will be 6 over negative 6. 6 divided by negative 6 equals negative 1. Okay. So I have a positive number here for line 1, which tells me if I'm reading left to right, I'm going to be going up. And sure enough, left to right, I am going up. I have a negative slope on my second line, line 2, which tells me from left to right, I'm going to be going down. And sure enough, I am. Okay. So I don't know if these are right, but I do know that they're at least going in the right direction. Okay. So I have my two slopes, line 1 and line 2. That's step 1. Step 2, figure out the y-intercept of both. Remember, y-intercept was b equals y minus mx. Again, two operations, line 1, line 2. B equals y minus mx. All right, so I pick any point I want on line 1. Let's pick point 1,5. So it'll be 5 minus 1. And my slope for that line 1 was 0.357. 0.357. If I do the math for this, make sure I'm doing it right. 0.357 times 1, obviously 5 minus 0.37 equals 5. 5 minus 4.643. Yep. 4.643. This is my y-intercept of line 1. Line 2, b equals y minus mx. B equals, pick any point I want. I'm going to choose 411. So it'll be 11 minus, my slope for line 1 was -1 times 4. So this would be 11 minus 4, 11 plus 4, b equals 15. Okay. So what does this tell us? Line 1, if I were to extend that further out this way, it would cross my y-axis at 4.643. Okay, right in between 5 and 4 is where it would hit my y-axis. If I were to extend this line 2, keep going up, I would intercept my y-axis at 0.15. That's what this is telling me, okay? So step 1, I got both of my slopes. And step 2, I got both of my y-intercepts. From that information, now I can use my slope-intercept form, set them equal, and it's going to reveal my x value. So let's do that in step 3. Okay. So line 1, line 2. mx plus b equals mx plus b. My slope of line 1 was 0.357. X, I have to use any point no, sorry. That's what we're solving for. X plus my y-intercept of line 1 was 4.643. 4.643 equals slope of line 2, which was 15, I think. No, -1, sorry, -1. X plus my y-intercept of line 2 was 15. Okay. So all I'm going to do here is I'm going to solve for x. So I'm going to move my 4 over. So it'd be 0.357x equals negative 1x plus, see, 15 minus 4.643 equals 10.357. Divide that side by negative 1, 0.357 divided by 1 negative. Negative 0.357x equals 10.357. Divide each side by negative 0.357. And x is going to equal, store 1, 10.357 divided by, recall 1. Do it again, hold on. 10.357 divided by 0.357. Did something wrong here. Let me try that one. 15 minus 4.643. Oh, damn it. Sorry. I have to add that 1. I'm not going to divide. I'm adding 1 over here. So I'm bringing this over here. So it's going to be 1.357 equals x equals 10.357. Now divide each side by 1.357. X will equal, make sure, 10.357 divided by, there we go, 7.6322. Okay. So I know now the x value of my point of intersection. That's what this has revealed. Okay. So I set my slope intercept forms of each line equal to each other. Solved for x. Now I know that my 2 lines this point right here, I know the x value of it is 7.632. I still don't know my y value, but I do know where they cross is going to be at 7.632. All right. So the final step, step 4, is going to be utilizing that the y-intercept form, which is y equals mx plus b. And what I do here is I can use any slope from any line, and whatever line I choose, I'm going to have to use that same line's y-intercept, and I'm going to plug in this x value for my value here. So I chose line 2. Let's choose line 1 to show how it works either way. Okay. So line 1's slope was 0.357. I know my x value is going to have to be this, 7.632. And my y-intercept of line 1 was, I don't remember. Y-intercept was 4.643. 4.643. All right. If I solve for y with all this, I'm going to get my y value. Let's see if it works. 0.357 times 7.632 equals that, plus 4.643 equals y equals 7.368 rounding. So that's my y value now. So that same point, my y value will be 7.368. So this line and this line cross at one point, and the value of that point is 7.632 x and 7.368 y. Okay, and it does make sense. It's about halfway between 1 and 15, 7, and it's about halfway between 11 and 5. Well, it's at a pretty steep one slope, so I'll have to do, it's almost like the hypotenuse between these two. But on the y-axis, it should be between 4 and 7, and that's about right. Okay, I'm sorry, 4 and 10. It's about 7, which is right, midway. All right. So step 1, get the slope for each line. Step 2, get the y-intercept for each line. Step 3, set the slope intercept forms equal to each other to reveal the x value. And then finally, step 4 is going to plug that x value into the y-intercept form of any line you choose. I chose line 2 here. Sorry, line 1 here. But on the yellow page on my PowerPoint, you see I chose line 2, and I got the same value. And that's because I changed my slope and my y-intercept, but I utilized the same x value, because those two lines only cross at one point. All right. Let me see. Finally, the coordinate of the intersection point is of the two straight lines is 7.362 and 7.368. Okay. Yep, that was all. So I want to show you all this too. Open this up. All right. This is a intersection point. You can find these on the internet too. They're pretty readily available. If you just type in intersecting line calculator, you'll find one. But I want to generate one myself. I like doing this because if you do this, if you generate a spreadsheet like this or something, you are you're making yourself truly understand the process, right? Because this you're basically telling it step by step exactly what to do with each number. So let's plug in the values for line 1 and see if we get the same answer. I haven't done this, so I hope it works. Let's see.
And for those that joined afterwards, I threw the link in the Dropbox chat again. And then those watching later, these files are in the Dropbox as well. So,
okay. Thank you.
Yep.
All right, let's see. So line 1, you got to stay organized. Line 1, I had 2 points. I had an X and a Y point. Line 1 was X value. This point was 1, 5. This point was 15, 10. Okay. So just this line, I generated my y-intercept right here and my slope. And these are matching what we found. So all this did was it took a difference in these y's divided by the difference in the x, and it created my slope. Then it punched in the y-intercept formula, which is b equals y minus mx. So I'm utilizing this slope, and any of these 2 points values plug in here, and I get my y-intercept. So this is where line 1 will cross the y-axis. Then line 2, it was 10, 5, and 4, 11. All right, so changing y over changing x, I get a slope of -1, which is what we got. And my y-intercept, where it crosses the y-axis, is 15. So that's right. The next step was setting the y-intercept forms equal to each other. And I'm going to be getting 7.63 is my value of my x. I plug that x value into the y-intercept form, utilizing either one of these lines, slope, intercept, or y-intercept and slope. I could choose either one. I don't know which one I chose here. Looks like I chose line 1s. And I get the values that are equal to what we just generated, okay? So if you go through this spreadsheet, it kind of lays out each steps. Step 1, step 2, step 3, step 4, and then you finally get your values, okay? Does everyone understand this?
I'm sure there's a few glassed over
Yeah.
and then there's a few wondering why we just can't take the spreadsheet into the test, but
Yeah, I know. Yeah,
I was gonna say, does anybody have specific questions, or maybe you want to go back and hit on something?
Yeah,
There's a
please
lot
do.
of moving parts to this, so
Yep.
like all of Dane's presentations.
Yeah, right.
There's a lot going on. So does anybody, you can unmute yourself. Where's our math whizzes? Rob. I know Jerry's in there.
Yeah, Jerry, don't unmute yourself, Jerry.
Rob's muted.
No, I'm joking, man.
Anybody? Nothing?
Yeah, I tried to break this down into 4 easy steps, just follow slope, y-intercept, set them equal, and then plug that value back into another slope intercept or y-intercept. And then my manual also does go, this is pretty much how I explain intersecting lines in the manual as well, but this is the same example I use in all. There's some really cool websites. They actually generate the lines for you, and I should have had one ready to go. Let me see. There was a really cool one. Let me see, really quick.
Yeah, you're good. We got time.
Yeah, I like the ones that actually show you the line. It draws a line for you too, Yeah, I'm not gonna be able to find one.
Of course, you're on the spot.
Yeah, I know. Yeah, that was a really, when I was doing this, should have saved it. Oh well. But yeah, like I said, I mean, it's not that difficult to math. It's just trying to really just stay organized is the biggest effort here,
Yeah.
I'd just chime in that this is part of the math that we saw when we were in, I don't know, 8th grade, 10th grade, somewhere in there.
Yeah.
That we scratched our heads when we went through it in class and then said, well, never going to use this again. And lo and behold, here it is. And just because this was couched in the framework of PLSS, center of section or center of quarter, it still works the same for other types of intersecting problems. It could be boundary, non-PLSS boundary bearing intersections. It could be even slope intersections for construction staking and trying to identify slope catch points and that sort of thing.
Yeah, I mean, yeah, there's a whole other aspect to this. You're kind of right. Like, I didn't think about that, but you have a point with some northing and easting here, which would be YX, by the way, remember. And then they give you a bearing, north 45, 15 east for 1,000 feet, let's say. Okay, well, in order to figure this out, you're going to have to generate the coordinate of this point up here, given this northing and easting and that bearing. And the way you're going to do that is you're going to do your latitudes and departures, and you're going to have this bearing essentially is going to give you that angle, right? Well, that angle minus 90 will give you this angle. So now you have your right triangle here, and you have your hypotenuse length, you have your angle, and from that you're going to be able to generate your departure right here and your latitude right here. And from that and that, you can generate your northing and easting at this point. So there might be another step in this. They might give you, on the test or something, they might not give you fine coordinates, nice coordinates. They might give you bearings and distances of this line and this line. You're going to have to, if they don't give you any coordinates, you're going to have to make some up. They're going to definitely not make you do that. But, they're going to have to give you coordinates of at least one of these. No, two of them, actually, because you're going to have two different lines. But from that, you're going to have to generate maybe coordinates of the other point. So that's a whole other step, and that's using right triangles again, with your bearing and your bearing and your distance as being your hypotenuse. From that bearing, you can figure out your angle. Now you have your right triangle set up to do your departure and your latitude. This value will be your X value. This value will be the Y value of this point up here. So that would be a whole other step just to get started with intersecting lines. This is just routine COGO, coordinate geometry. This is COGO is the backbone of all the math that we're going to have to sit here and do. That's essentially what COGO is. Double, single proportioning, the same situations can be applied there as well. Okay.
Yeah, Andrew Bowen chimed in the chat that he's teaching this method tomorrow for slope intercepts. So in that case, if you're working off, say, a road alignment, then your easting is your offset from center line, and your northing is your elevation. It's just a different way of manipulating the X and Y.
Yeah, you're reorienting it.
Yeah.
Yep.
You got to reorient that stuff in your head.
Yeah. Or I like to keep it flat and just have different values assigned to different things.
Yeah. One thing to keep in mind, and I really appreciate you saying it early on, is if you're in the field and you're doing math, you're probably doing something wrong. There's other problems going on where you're not finding other evidence. And
whenever you're,
and that
whenever you're doing boundary, for sure. If
yeah,
you're,
and that the proration being the last resort. And but that's one of the things that you will be tested on, because it's a math problem. It's easy to grade. Either you get it right or you don't, right?
yep,
But
yeah,
I recall hearing a story a number of years ago where the California board suspected a group of people who were all from the same geographic area at the same testing center of exam what do they call it, exam collusion. They were cheating on the test together,
yeah,
because they all came up with the same answer for a center of section. They came up with identical answers, all completely wrong.
huh,
Back in the days when the test was the longhand
Yeah.
style test.
yeah,
And what they figured out is the whole group of people were involved in a LS review, and the person that taught them how to do center of section completely blew it and said you intersect the section corners and the diagonals.
Oh,
no,
So
wow.
here, like 8 people did it just like they were taught, and didn't refer to the manual and go to the quarter corners, opposite quarter corners.
Oh my
Right.
gosh.
And they all got what would be the correct answer for the section corner intersections, but not for actually what they were trying to
so
accomplish.
he did,
Yeah.
Yeah. And think about that from like writing the test exam. Who would have thought, let's throw that sample in there, or example in there, like a multiple
Yeah.
choice question now, right? Like,
Right.
oh my gosh, that's crazy.
yeah.
And
I am, you're making me scared. I am correct, right, Trent? Like,
Yeah.
you are correct. So
okay.
do not do diagonals. It's
Yeah.
quarter corners.
You're funny.
Yeah, yeah.
So
Megan
Don't
Dane-
do that.
Megan Dane second guess himself.
but
Yeah,
so that's something that as students prepping for these exams, sure, we got between me and Jerry and a couple of the other gray-haired guys on here, and add in Trent, well, pretty soon we get to 200 years of experience. But add in Dane and we get 210 or 20. But
yeah. 202.
take these lessons and then go back to the manuals and see how, once you've seen it done on these mentoring Mondays or any type of training session that you get, go back to the manuals and make sure that what you're learning makes sense from the manual perspective as well.
But
Yep.
throw in a couple of comments here. Trent, that wrong answer, when I write exams, those wrong answers are on there.
All right, you go,
Yeah,
Jerry.
on purpose. But in Wisconsin, we have the added flavor that during about a 12-year period in the mid 1800s, we had two other methods for setting center of section that was defined by state law: equidistant east-west, which is a piece of cake, but then equidistant east-west and equidistant north-south at the same time, which is a bit of a challenge.
Wow.
That is on our jurisdictional exam. It's not on a national exam, because the national one's always been connection of opposite quarter corners.
Right.
So yeah. The other thing that, as I was putting together, modernizing my presentation on field notes for the presentation later on, so which nobody's going to show up to, because everybody knows we don't need field notes anymore. But this harkens back to something Rob mentioned. Um, we, if we depend too much on software, computers, and data collectors to do this, then if you wind up in court someday and are asked to justify how you decided to use that solution, I don't think saying, well, I did what the software told me to do is going to be a legitimate. So you got to remember that when you buy software, as soon as you turn that seal off, you've automatically agreed to the user agreement, which says that you assume all responsibility for using that software. So there's a lot of stuff that if you don't understand the fundamentals, surveying is beyond technology. It's not just technology, it's understanding the basis for that technology. So this kind of stuff here, I think, is really important.
Yeah.
Absolutely, Jerry. Up here in Canada, if you can't prove your calculations, they aren't valid. You could use all the data collector CAD software you want, but if you can't prove it, it's invalid in court.
Yeah, documentation is key. And hauling around the data collector is not documentation. That's
Yeah.
we're on some really slippery slopes here.
Yeah. Mike had put in a comment, holy crap, it's both funny and sad about those students. And so that is amazing. One, that the teacher teaching the LS review exam, part of that process, was allowed to teach that is even crazier. But
Yeah.
Wild.
The good news on that was that the students didn't get in trouble for violating the exam.
Yeah, exactly.
The exam. Once they got contacted and interviewed about it, and the actual person who gave that instruction was contacted afterwards, and it was suggested that he freshen up his knowledge base before teaching that again.
Yeah.
Yeah.
Oh my gosh. So we did week 82 was single and double proportionings, but I guess there's partly some issues with the video, maybe on your drawing side of that. But if you want to, I see you have that one pulled up now in your spreadsheet, so we can kind of reference
The
back to
single
that.
double proportioning?
Yeah. We kind of
Yeah.
read through a couple of these, couple of your
Yeah.
spreadsheets with that, and then we can.
Okay.
That'd be cool.
Yeah. So I created this one. So when you think of double proportioning, again, double proportioning, you're going to be double proportioning section corners that are not on township lines. Okay. And again, if you're using math, something's wrong. You have zero evidence that corners what they call lost. But so you're going to have 4 lines coming into your corner that you're trying to reestablish. You're going to have line 1. This line right here from the north point down to the section. You'll have line 2 from the south point up to the lost section. Line 3, which is going to be from this point to the section, and then line 4 from this point to the section, to the lost section. So think of it as 4 different lines all converging at one spot. And all this spreadsheet's going to do is, first it generates the angle from the record boundary, from the record bearing. So this bearing right here, I'm going to look at the GLO plat. I'm going to get a bearing, plug my bearing in, degrees, minutes, seconds. It's going to convert it to an angle. This is the distance that I have to plug in. That's going to be provided per the GLO note. From that bearing and that distance, I can generate a record latitude, which would be a proportion of this whole north-south line. That's what this value is right here. That's just simply from the bearing and the distance. And this is generated just by finding out the latitude, which is an operation of right triangles. It's going to be this angle and it'll be the cosine of that angle and with this hypotenuse of 40 chains, let's say, okay? The same exact thing happens to this south line. Plug in that bearing. It's going to generate an angle. From that angle, I can do my right triangle operations to figure out my latitude for this south chunk right here. So I have my south chunk and my north chunk of my north-south line. These are my record proportions. If I combine those two, I get my total record distance, latitudinally speaking, from point to point. That's what this is. That's just a summation of this part, this north part, and this south part, okay? I have to do the exact same thing I did here for this east-west line. Plug in my bearing, plug in my distance. I'm going to generate, now I'm looking only for departure. I don't care about latitude anymore. When I'm working on my east-west line, I just care about my departure. So I'm going to do my sine now of this angle. So my bearing and my record distance is going to generate a record proportional departure. So that is how far I go from my section corner to that point, latitudinally or horizontally speaking only. I do it again for this half over here. Now I have my two chunks. If I add them up, I have my total departure from point to point on my record line. So all that we've done in this portion right here is just record information, okay? I haven't even looked at my northings and my eastings of my measured information yet, okay? This is purely record data. Then I go into my measurements now. That's what this section's about. So for this is pretty easy. This is just saying, how far do I change from this point to that point purely in a latitudinal Y or northing direction? That's simple. I'm just going to take this northing, subtract that northing. The difference between the two is how far I've traveled from point to point in a perfect vertical line, okay? That point minus that point is going to give me that value. So from point to point, straight line from point to point, vertical straight line is 5,177 feet, okay? Well, I do the same thing for my east-west. Now I don't care how much I change latitudinally or in a northing direction. All I care about is how far do I change from point to point in an easterly along my x-axis, a perfectly horizontal line. Well, that would just be taking this easting and subtracting that easting. That's all that this is doing. So from point to point there, I'm changing 5,276.61 feet, okay? So this section is purely measurements. What are my measured values? This is purely recorded values. Then we start to combine the two. That's what this matrix is about. And I have this all in the manual and we've done this before, but I start filling in this matrix. I got to do the matrix twice. One from my north-south line, one for my east-west line. So I plug in my measured total, which was this value here, and my record total, which was this value here. I'm just filling in these squares right here. And eventually I'm going to be solving for my measured proportional, which is what I want to figure out. How far am I going to have to go up from my measurement or down from my measurement? So I solve for my Y value here and my X value here. I do the exact same thing for my east-west line with these values. I get a value for my Y, I get a value for my X. If I combine the two, I have my intersection point. And the beauty of doing it this way, as I explained in the manual and stuff, the beauty of it doing it this way is if you deal with the departures and the latitudes from the very beginning, as opposed to waiting and doing them at the end, you don't have to worry about doing that, the cardinal equivalence of the point. You're essentially doing the cardinal equivalence of that value the whole way through, okay? By default, you are creating your cardinal equivalent if you only deal with your latitudes and your departures the whole time, okay? So you do have this, and hopefully I can go and sit and redo this single double proportioning at some point, Trent, if you want to wait a year or so to make sure. But yeah, this stuff can get pretty confusing. Again, it's not hard math, it's just trying to stay organized, you know? And again, by me creating this, it really makes you really go step by step. It really kind of solidifies the process in your head, you know? So now you just enter in all the red digits or values you have to enter.
Very cool. Yeah, it's great for just checking your math and that kind of stuff. That's awesome. As you're studying, doing this from a study standpoint. Yeah.
Yeah, definitely.
Very cool. What was the third one? Oh, section 6, right?
Yeah, section 6 breakdown. That was a lot easier than I thought. So you have your section 6, and you have really the only values you really need to look at on this whole page are going to be these highlighted values, and you can get these values from this number here too, from your record information. If you know the rules, the west half and the west half of the west half, the west half and the west half of the west half are going to get what they're given. They're going to get their 20, 20, 20. So a lot of these calculations, you don't have to do math. You just got to know the rule, right? So automatically I know 1, 2, 3, 4, and 5, all those values, they're all going to be 20. I already know that. The same thing goes for this. 6, 7, 8, 9, and 10, I know their values are all 20s. The only ones I really got to figure out are going to be this B, A, and C, and E, D, and F. So, and all that is just averaging the average. So to find A, you just average that distance and that distance. That'll give you A. To find B, you have to average this distance and what you just found for the middle distance. So it's an average of an average for this one. And the same thing for letter C. It'll be the given distance averaged against this average over here. So it's an average of an average there. So this is just an average. And then these two are averages of averages. Okay. And the same, it's the mirror image just in this direction. So you find the average of D for D. And then for finding E, you would be the average of D and this given. And for F would be the average of D and this given. And that's all plugged in here. So for this, really, if you notice, there's only 4 red numbers. You only have to plug in 4 numbers, and I can give you the answer for every single one of these lines and their areas as well. Okay. So to find the area, so you have this square right here. Let's say lot 3. Okay. Lot 3, to find the area of an irregular shaped polygon, it's still length time width, but it's really going to be the average of the 2 lengths times the average of the 2 widths. Does that make sense? So you got to find the average of your 2 width lines and the average of your 2 length lines Then you multiply those together to find your area. And that's all that this is doing down here. It's just finding the average of the two lines, multiplying them together, and you're going to get your area. So again, this whole spreadsheet all depends on these 4 point values, these 4 length values, which are going to be given to you on that GLO plat in one way, shape, or form. They're either going to be stated or they're going to tell you that whole distance. But you know that whole distance, that whole record distance, 60 of it, 60 chains of that distance is going to be given away to this line, and this line. All right. And then the same thing goes for here. Of this whole distance here, 60 chains of it is gone. It's given here, here, and here. So whatever's left over or excess, either excess or deficiency, is going to be assigned here. And I think I'm doing this one next time. Is that right?
Yeah, that's what I was just gonna look and see what our next one was. It is survey statistics. That's the
Oh
next
yeah. Oh yeah. That's a good one. It's not this.
and then May 1st, we're doing traverse adjustments.
Oh
So-
wow. All right. Yeah. So it'd be a ways away then, but
Yeah.
we'll get to it eventually.
Okay. Yeah. Yeah. We can plug it in we can look at your schedule for the 1st of June. So,
Okay.
Okay.
All right, guys.
very cool.
Come in.
Did that open up any more questions for anybody?
Do you have just Frederick?
I'm coming right now. That's my son asking.
Yeah. He's like, hey, it's dinner time. Let's go.
Yeah.
All right. Well, as always, Dane, love your passion, love your teaching styles. It's great. There was tons of accolades in the chat earlier, but
Yeah. Thank
love
y'all
the-
very much.
Yep. Love the new stuff. We'll definitely grab that section 6 coming up, but thanks for going over
Yeah.
those spreadsheets. Those are in the Dropbox. I'll share all that stuff out as well. So
Yeah. Please. Yeah. Get them going on that when we get
Yep.
around to it. Yeah. Next time is statistics. That'll be a good one.
some more glassed over eyes.
Yeah.
All right. Have
All right,
a
thank y'all.
have a great week in Hawaii next week. Enjoy.
Yeah.
All right,
Hopefully we
guys.
make it, man. All
You'll
right.
be
Thank
fine. You'll be fine. All right, guys. Have a good night.
See
Have a
ya.
good week, everybody.
Thanks, guys. See
you.
ya.
Bye.
Bye.